Chapter 10. Abstract Thinking. With this new thinking, Thales was the first to abstract and formulate the rules of geometry. By his method, he was also liberating people's minds. How well his fellow Greeks realized this can be seen in the most famous of all the stories about Thales. It concerns a sensational event that occurred in the midst of a battle. In 585 BC, the Medes and Lydians were in the 6th year of a stubborn war. Suddenly, broad daylight turned to darkness. The sun gave no light. Terrified out of their wits by the fearful gloom, the warring hosts stopped killing each other and they immediately concluded a peace. History says that this was an eclipse of the sun. Legend says that Thales had forecasted it accurately through the pattern in the records he studied in Babylon. Scholars have doubted that Thales predicted the eclipse, but recent studies suggest he used an early imperfect method known as to Assyrian court astronomers. Either way, the point of the story is the same. The Greeks believed Thales had made the prediction, in other words, that such a prediction was possible. Thales' studying of reasoning had taught them to look for an orderly pattern in nature, instead of imagining that an eclipse came about when Apollo, the sun god, hit his face in displeasure. So great indeed was Thales' fame that he was ranked as the first of the fabled 7 wise men of Greece. He was supposed to have originated the motto, "Know yourself," but "think for yourself" sounds more like Thales. He taught people to do just that with his new abstract rules. Before him, geometry had consisted of isolated observations, ways grasped from trial and error for handling and calculating material things. Thales showed the need of a careful demonstration based on a logical sequence of geometric concepts abstracted from material things. To explain how he did this, we shall show Thales actually teaching. There is no evidence that he did, but tradition gives him at least 2 famous pupils, and he was not a solitary thinker, but a busy man of affairs. So he might have expounded his new concepts in some such scenes as those we were about to describe. Thales teaching Babylonian angles and Egyptian measures. When Thales returned from abroad, he probably brought interesting and even expensive curios for his friends. Perhaps Mesopotamian seals and amulets, Egyptian jewelry and glass. But the most valuable contribution he brought back to his homeland was the wealth of new ideas in his head, the string in his pocket, and the memory of shadows on the sand. Picture the amusement when his friends gathered around him to hear about his travels, and Thales took out a piece of string and began to draw circles on the ground, but not everyone laughed. Some friends were fascinated as he made more circles and showed how the Babylonians divided them, or he would knot the string and show how the Egyptians made a right-angled triangle and squared off their rectangular fields. Or he would reveal his new thoughts about the sun-made right-angled triangles, the abstract ones made by the bright ray, the object and the shadow. Soon we may imagine a small group assembled, Thales teaching and expounding, and his friends gradually joining in the discussion. They met in an open-air place with white sand on the ground and poles of different heights to cast different length shadows. Thales would draw circles and triangles and straight lines on the sand with a string and a straight edge. Tell in which country he had studied these forms and explain his new ideas about them. The others would sit and stand and pace in the sun. They would study the diagrams, watch the shadows, swing the string, ask questions, and argue. It was like an exciting new game, the game of string, straight edge, and shadows. Every game has its rules, so the eager players would go into huddles to discuss the rules and reasons and to reach agreements. These rules, Thales showed them, had to be reached through careful step-by-step reasoning based on agreements and definitions. It's hard to imagine how thrilling this new intellectual game must have been to its participants. For the first time in history, people were doing sustained abstract thinking about the principles of line and form. The Babylonians and Egyptians had used these right angles, levels, divided circles, and geometric designs. Thales and his friends were now thinking about them, thinking in the abstract, as he had when he measured the pyramid. Angles in a circle and different kinds of triangles. Thales explained the Babylonian division of the circle into 360 degrees and showed how the same measurements applied to angles. Mostly they could see these things for themselves, with just a few definitions and rules. A circle is a closed curve on which every point is equally distant from the point within, called the center. Such a closed curve is called the circumference, and the radius of the circle is the distance from the center to the circumference. A diameter of the circle is a straight line passing through the center, dividing the circumference into two equal parts, each of 180 degrees. By using a piece of string longer than the radius and swinging equal intersecting arcs from each end of the diameter, another line called a perpendicular can be drawn through the center to divide the circle into 4 equal parts, each of 90 degrees. Arcs, marked off at successive points on the circumference with string the same length as the radius, divide the circle into 6 equal parts, each of 60 degrees. From these definitions, it was obvious that the space surrounding any point may be divided into 360 degrees. A straight line, such as a diameter drawn through a point, is called a straight angle and has 180 degrees. A perpendicular to this straight line forms 2 angles, each of 90 degrees, called a right angle. Angles adding up to a straight line total 180 degrees. Whether they are 2 right angles, 2 uneven angles, or more than 2 angles. Speaking of the Egyptian rope triangles, Thales reminded his friends that a long rope knotted at intervals of 10 paces would form a right angle when stretched on the earth with sides of 3, 4, and 5 units. And so would a shorter rope knotted at 1 pace intervals, as would a small cord knotted at intervals the width of a person's hand. The triangles would differ greatly in size, but they would be similar. Each would be a right-angled triangle with sides in the proportion 3:4:5. More carefully now. Thales went over the rules for measuring the height of objects from sun-made imaginary right-angled triangles, as he had done at the Great Pyramid. When their corresponding angles are equal, the right-angled triangles are similar, and their corresponding sides are in proportion. The study of the Egyptian level revealed that the string hanging from the vertex of a triangle is perpendicular to the base and divides the triangle into two right-angled triangles of exactly the same size. Then it became clear that any triangle which has two equal sides must have equal base angles. Such a triangle is called isosceles, which in Greek means equal legs. In an isosceles triangle, the two base angles are equal. From a familiar pattern found by dividing a circle into 6 equal parts, an unexpected new relation emerged. All 3 sides in each of the triangles are equal to the length of the radius, and all 3 angles are equal to 60 degrees. In an equilateral, equal-sided triangle, each interior angle is 60 degrees, and the sum of the 3 interior angles is 180 degrees. Other rules of angles. Since 2 lines perpendicular to each other form 4 equal angles of 90 degrees, it was easy to see that when any 2 straight lines cross, the 2 pairs of opposite angles are equal. A diagonal line cuts 2 parallel lines at the same angle, thus forming 2 pairs of equal angles smaller than 90 degrees and 2 pairs of equal angles larger than 90 degrees. The alternate interior angles formed by a diagonal cutting 2 parallel lines are equal. By constructing a line parallel to the base of any triangle, said Thales, we can see that the sum of the angles in any triangle is equal to 180 degrees. And in that any right-angled triangle, since the right angle is 90 degrees, the sum of the other 2 angles is 90 degrees. Finally, Thales showed his friends how to combine these rules to make an important discovery about semicircles. He pointed out that 2 straight lines drawn from any point on a semicircle to the ends of the diameter form an enclosed angle of 90 degrees. Can you see how he might have done it? A radius drawn to the point on the semicircle divides the inscribed triangle into 2 isosceles triangles. Since each has 2 equal sides, we know that each isosceles triangle has equal base angles. And as the inscribed angle is equal to the sum of base angles, 2 times the sum must be equal to 180 degrees. Then the inscribed angle is 1/2 of 180 or 90 degrees. Any angle inscribed in a semicircle is a right angle. In spite of his interest in abstract rules, Thales was always a practical man who knew how to apply a rule since he got hold of it. Remember the story of the oil presses. After he had formulated his rules about triangles, he used them to measure the distance of ships out at sea, which was quite valuable for merchants. He and his Ionian contemporaries were not only philosophers, but inventors or reinventors as well. There was Theodorus, who perfected the Egyptian level into the Greek siphon, and Anaximander, who used the shadow pole for astronomical measurements. That was as much a part of Ionian thought as speculation on the basic substance of the universe, and Thales was the first to excel in each branch of Ionian natural philosophy. So this practical merchant was a true pioneer of rational thinking in his view of nature and especially his work on geometry. It was he who formulated the very earliest rules for the new game of string, straightedge, and shadows. As the first to, by building rule upon rule, he started the method of deductive reasoning, which would be continued by later geometers.